So we're going to talk about some applied optimization word problems. And most of what we're doing in this section is really just going to be algebra. We're just going to be applying maximum and minimum values to it. And remember, the max and min values occur when the derivative is equal to 0. And if you want to find that actual maximum or min, you take that critical number you determine from getting the derivative equal to 0, and you plug it into the original function that you have that models your situation. So the hard part about word problems for students is that it's difficult to decode. So, the first step when you're solving word problems, make sure you read it until you understand it. Then you want to look at what's given. What is the unknown quantity? Because the unknown quantity, if you can determine that, you will know how to set up your variables. You know what you're looking for. A lot of these problems, you're going to need to draw a picture. Again, using variables appropriately. We want to list everything that's related in the picture and identify the variables so that we know what they mean. We'll generally be setting up an equation. And once we have that equation, the equation may require some manipulation to make it what we want. So sometimes we may have two equations and two variables and we need to sub one into the other. So after we have that equation, it's basically going to be the same thing every time. We're going to take those critical points, and the critical points are going to come from that first derivative being equal to 0. We may have endpoints or restrictions on the domain, and that may need to be considered as well. Okay? But at this point, we use the first and sometimes second derivative to determine, the solution to what we're being asked. So let's jump in and do a problem. So here we have a problem. We're going to design a box with a lid. We have a piece of cardboard measuring 10 by 15 inches, and we need to create the box with the lid out of that piece of cardboard. Two equal squares are removed from these two corners, so we're talking about squares in that region, of a 10-inch side as shown in the figure, and then two equal rectangles are removed from the other two corners. So this is the shape that we're dealing with, and we're cutting this out of something that was originally 10 by 15, and we want to maximize the volume of this box so we can maximize our contents. So let's read the rest of the problem and see what we need to find. First, we're going to set up a formula for the volume of the box. Then we will determine the domain of V for the problem situation and the graph of V over this domain. And we'll use a graphical method to find a maximum volume and the value of X that creates it. All right, and then what we'll do is we will confirm this analytically. We'll use derivatives in order to help us solve this with calculus. So setting up a formula for the volume of the box, and it's helpful for us to visualize what we're creating. We're creating a box that is, essentially rectangular. And each piece of our box here, we have a length, width, and a height, right? So, for example, we have a base. I've highlighted it in red. That might represent this piece of our box. And what is the length of that base? So we have cut some pieces out. In this case, we have 10 minus 2x being the length of that side. All right. We have another side of our base. This is like the length and width of the base area. And we need to figure out how wide that piece is. So the length of this side here, it's going to be 15 take away 2x. And so 15 take away 2x gives us both the length of that base and the lid. So we have two pieces. So we're going to take this and say 15 minus 2x over 2. And then if we visualize, folding this up, we're going to have all of these different heights, right? And so that height in this situation is x. And when you're setting this up, you might not have all of the same variables. This is where some substitution may come into play. But in this case, our rectangular box, notice that my length, width, and height are all have the same variable x. So for part A, the volume of my box, V of x, well, that's going to equal the length times the width times the height. So I've got 10 minus 2x times x times 15 minus 2x over 2. All right, and this can be simplified with some quick multiplication. So my answer for A, we end up with 2x cubed minus 25x squared plus 75x. So this represents a formula, volume in terms of x, for my box. So when we think about domain, what are the possible values that x could be? Okay? So thinking about domain, thinking about our possible value for x. So look back at the picture and say, well, what does x represent? X represents what we have cut out. And how big can I actually cut x out realistically? How big could that value be? And because our shorter side is 10, the largest that could be would be half of 10 because I've got to cut it out on either side. So for part B, my x values, it's only possible for them to be 0 to 5. And I can't actually cut 0 out, and I can't actually cut 5 out because then it would just make it go away. So the x value that I cut out is something between 0 and 5. So solving this graphically, we would create the graph plugging our volume function into the graphing calculator and looking at it over its domain. So what I've done here is I went to my Desmos on my tablet and I pulled up the graph, and what you would be typing in your y1 is y1 equals 2x cubed minus 25x squared plus 75x. And if you press on your calculator second and then you choose the option to calculate, the fourth option you see there offers you the option to choose a maximum. So here is my curve of my volume. On the x-axis, I've set my window to go from 0 to 5, and that's in inches. On my y-axis, we're talking about a volume, a 0 volume box, up to a maximum. I set mine to, 75 or 80. Okay, so we've got volume on the y-axis. And this point right here is the max. So what we see is that the max volume, my y value, is 66.019 inches cubed when my x value, when x is 1.962 inches. So that's what I'm cutting out of the side. Now, we didn't do any calculus here. We just did this with algebra and our calculator. But I'm going to confirm what we know using calculus. So for part D of this problem, we're going to confirm that max or min analytically. So we're going to confirm this with calculus. All right, so in order to do this, we've got our volume function. V of x is 2x cubed minus 25x squared plus 75x. So that means v prime of x, my volume derivative, is 6x squared minus 50x plus 75. So in order to solve for our critical numbers, where that max or min might occur, we set the derivative equal to 0. In this case, I can't factor this, so we use our quadratic formula. So negative b is negative 50 plus or minus the square root of negative 50 squared minus 4 times 6 times positive 75 all over 2 times 6. And simplifying this, I get two values for x. I get approximately 1.962 or 6.37. So these are the two solutions to this quadratic equation. However, 6.37 is outside the domain. It's not possible for me to cut two 6.3 or 6-inch pieces out of 10 inches because there's simply not enough space. So this is the critical number on my domain where the max occurs at 1.962. All right, what is the volume? That volume is found by taking that 1.962 and plugging it into the volume equation, not the derivative. So if I were to do that, I would say we've got a volume is 2. So we've got 2 times 1.962 cubed minus 25 times that 1.962 squared plus 75 times 1.962. And in this case, we get v of 1.96 is that 66.019, and that would be inches cubed. So this is how we can solve this applied optimization problem. We have an application problem, optimizing, finding that max or min using our calculus. Okay? So we still have our calculator. We can use that. The hard part is setting up the equation, and that's really going to be using a lot of algebra. So I have one more thing that I want to talk about here. Prove this is a max. And in some of our previous sections, we talked about the second derivative test for extreme values. So I could find my second derivative, v double prime of x, equals, that would be 12x minus 50. And if I evaluate v double prime of x at that critical number, my output is negative. So what the second derivative test for max and min says is if you evaluate the second derivative at your critical number, if you get a negative output from the second derivative, that proves that that critical number represents a max. Okay?